Buckle up, everybody, because today we are going deep into quantum mechanics.
That's right.
It's going to be a wild ride.
Yeah, it is.
So we are talking all about quantum entanglement and teleportation,
Okay.
with our main source material being Quantum Entanglement and Teleportation by Ivan B. Georgevich.
Great book.
Oh, yeah. So you've probably heard
A little bit about.
this stuff before.
Yeah.
Spooky action at a distance, right?
Yeah. That's the one.
Particles linked across space and time.
Mm-hmm.
All that fun stuff.
Yeah.
But we're going to go way beyond that.
Way beyond.
Like into some really recent advancements and like
absolutely.
what this could mean for the future of communication.
Computation.
And like even beyond that.
Yeah, this is
Some really mind-bending stuff.
I find it fascinating because even though these concepts seem like out of science fiction, really, they're not just theoretical anymore.
Right. They're happy.
This stuff's being seen in labs
Right.
around the world.
And it really could change everything.
It really could.
So let's start with the spooky action thing.
Yeah.
Right? Quantum entanglement.
Yeah.
So we're talking about two particles that are so closely linked,
Yes.
they act like one, no matter how far apart they are.
That's exactly right.
So it's like
an invisible
thread connecting them.
It is like that. Yeah, it's like this invisible thread connecting them.
Whoa.
And here's where it gets really mind-boggling, okay?
Okay.
When you measure the state of one of those particles, it instantly determines the state of the other one.
Whoa.
Even if they're light years apart.
What? Yeah.
So that means...
It defies all of our classical intuition about locality.
Right.
This idea that an object can only be influenced by its immediate surroundings.
Right.
But this isn't the case with
entanglement.
Yeah, it's almost like they're
communicating faster than the speed of light. That's the thing.
But how is that even
possible?
Yeah.
It doesn't. It's one of the biggest mysteries.
It really is.
Of quantum mechanics.
Yeah.
I mean, it challenges our understanding of causality.
That's causality.
So causality is this idea that a cause must precede its effect.
Okay, yeah.
So how can one particle know what's happening to its entangled partner instantaneously?
Whoa.
Yeah, it's a question that physicists are still
grappling with.
Yeah, exactly.
It's like, what came first, the chicken or the egg?
Kinda, yeah.
But on a quantum level.
On a much grander scale.
So, okay, entanglement is already a lot to wrap our heads around.
Sure.
But then we get into teleportation.
Right.
And when I hear teleportation, I'm thinking Star Trek.
I know exactly what you mean.
Beam me up, Scotty.
Yeah, right.
But we're not talking about that.
We're not talking about that.
Yeah, we're not talking about physically beaming matter from one place to another. So then what are we talking about?
What we're talking about is transmitting information.
Okay.
Okay, so it's like a blueprint.
Right.
That allows you to perfectly recreate a quantum state somewhere else.
So instead of beaming up a person.
Yes.
We're beaming up the information.
That makes up that person.
To recreate them.
Recreate them.
Somewhere else.
Exactly.
It's like sending a recipe for a cake.
I was going to say that.
Rather than the cake itself.
Oh, that's a perfect analogy.
Okay, so let's break down
how
this teleportation process actually works.
Right.
So you start with two entangled particles.
Right.
One stays with the sender.
Right.
The other goes to the receiver. Sender takes the particle holding the information they want to teleport.
Yes.
And they make a special measurement on it along with their entangled particle.
Yes.
And that's where the magic happens.
That's where the magic happens.
So what happens next?
So those measurement results,
okay,
which are just classical bits of information, they get sent to the receiver.
So like a text message?
Yeah, kind of like a text message.
Right. Okay.
And here's the amazing part.
Okay.
The receiver uses that information along with their own entangled particle to reconstruct the original quantum state.
So it's like...
So the information has basically been teleported.
From one particle to another.
Exactly.
Without the particles themselves actually moving.
That's right.
That's incredible.
It is pretty incredible.
And, speaking of incredible, our source material talks about some huge breakthroughs in this field.
Huge.
Like scientists have actually teleported quantum information over 44 kilometers using fiber optic cables.
It's amazing.
That's like...
I can't even...
That's a long way.
Yeah. It is.
So it's not just like in a tiny little lab anymore.
No, it's not just a...
It's moving out.
Real world distance.
It's becoming real.
And it's only getting better.
Absolutely. And the progress doesn't stop there.
Oh, there's more. There's more.
Tell me more.
So researchers at ICFO...
Who are they?
They're Research Institute.
Cool.
They're using a system with something called multiplexed quantum memories.
Okay, that sounds complicated.
It is a little bit complicated, but basically they were able to teleport a photon's state.
What's a photon?
So a photon's a particle of light onto a solid-state qubit over a kilometer.
Okay, slow down.
Right.
What's a qubit?
A qubit's short for quantum bit.
Okay.
And it's basically the basic unit of information in quantum computing.
Got it.
Okay.
And solid-state qubits?
Yeah.
They're different from photons.
So photons are always on the move.
Okay.
But solid-state qubits can store quantum information for much longer.
Oh, that's interesting.
So
they're more like a hard drive or something.
Exactly, which makes them much more practical for building quantum computers.
That makes sense.
Yeah.
So is this research a big deal then?
It's a huge deal.
Really?
Yeah, because teleporting onto a solid-state qubit is a major step toward more stable and scalable quantum systems.
So like less fragile?
Yeah, less fragile, more...
Easier to work with.
Easier to work with, exactly.
So it's not just photons and qubits?
No, not at all.
What else are they doing this with?
We've seen teleportation demonstrated with atoms.
Wow.
Superconducting circuits.
What are those?
They're electrical circuits that operate at extremely low temperatures.
Okay.
Where they exhibit quantum mechanical behavior.
Interesting.
Yeah.
So it's really across the board.
It really is.
That's amazing.
I know this field is advancing so rapidly.
Yeah. It seems like every day there's something new.
Absolutely.
So, okay, we talked about what entanglement and teleportation are.
We have.
And how they work.
Yeah.
Now, the big question...
Hit me.
Why should we care?
That is the big question.
What's the point of all this?
What's the point of all this quantum wizardry?
Yeah.
Well, one area that's already being explored is quantum communication.
So like how we talk to each other.
Exact. Imagine a world where we could send information instantaneously and securely.
That's a big deal.
Across vast distances using entangled particles.
So like no more lag.
No more lag.
When I'm playing video games.
Exact.
That would be amazing.
And it's not just for gaming.
Oh, yeah?
This is the vision behind the quantum internet.
What's that?
It's this global network of quantum computers.
Whoa.
All connected by entanglement.
Okay.
For instantaneous secure communication.
So it's like a super secure, super fast internet.
Basically.
Yeah. No more buffering.
No more buffering.
Sign me up.
And the security aspect is even more revolutionary.
How so?
Because quantum key distribution, or QKD, uses entanglement to create encryption keys that are theoretically unbreakable.
Whoa, so like no more data breaches?
No more data breaches.
That would change the world.
It really would.
So it's like a secret code that's impossible to crack.
Exactly.
But I also understand that entanglement is crucial.
It is.
For quantum computing.
Yeah.
So how does that work?
Well, entanglement is what allows us to create something called multi-qubit gates.
Multi-qubit gates, what are those?
Well, think of them like the logic gates in a classical computer.
Okay.
But on a quantum level.
Okay.
These gates enable quantum computers to perform computations that are impossible for even the most powerful classical computers.
So we're talking about computers that could solve problems that would take normal computers.
Millions of years.
Millions of years?
To solve
what kind of problems are we talking about?
We're talking about problems like designing new materials.
Okay.
Simulating complex molecules for drug discovery.
Wow.
Or breaking modern encryption algorithms.
Oh, no.
Yeah.
There's always a downside.
There's always a downside, but the potential applications are vast.
It's true.
And could revolutionize fields like medicine, material science, and artificial intelligence.
So basically all the big ones.
Basically, yeah.
Wow. And teleportation plays a role in all this, too.
It does. So teleportation techniques are used in quantum error correction.
What's that?
So because these quantum states are very fragile, they're susceptible to noise and errors.
So this helps protect them?
Yes. Teleportation can help protect those fragile quantum states.
It's like a shield.
Yeah, kind of like a shield.
That's incredible.
It is pretty incredible.
But there's got to be some challenges, right?
You're always challenged.
It can't all be smooth sailing.
If it were easy, everyone would be doing it.
Yeah.
So one of the biggest hurdles is maintaining the coherence of these quantum states.
What does that mean, coherence?
So basically, they're incredibly sensitive to any kind of environmental disturbance.
So like temperature changes or?
Temperature changes, vibrations, electromagnetic field.
Wow, so they have to be kept
Very isolated.
very isolated.
Yeah, think of it like trying to balance a pencil on its tip.
Oh, yeah.
Any slight vibration will knock it over.
Right.
And these quantum states are even more delicate than that.
Oh, my gosh.
And then on top of that, there's the challenge of scaling up these systems.
Right.
So we can handle more complex tasks.
Yeah.
And transmit over longer distances.
And integrate them with our existing technology.
Absolutely. We need to figure out how to bridge the gap
between the quantum world
and the classical world
for practical everyday application.
Oh, exactly.
It's like we're building this incredible, powerful machine.
Yeah.
But it's made of the most delicate china.
That's a great analogy.
Right.
Yeah.
But even so, the potential of entanglement and teleportation.
Oh, it's enormous.
It's truly transformative.
It is.
We could be talking about changing the way we communicate. Compute.
Yeah.
And maybe even the way we understand the very fabric of reality.
I like to think about it like this.
Okay.
If entanglement allows for instantaneous communication across vast distances, what does that tell us about our current understanding of space and time?
That's a big question.
It is a big question.
So are we wrong about...
It makes you wonder, right?
It really does.
Does it mean that our perception of space and time is fundamentally flawed? Or is there some deeper principle at play that we haven't even grasped yet?
It's like there's a whole other layer of reality that we're just starting to... Glimpse.
Yeah.
I don't know if I'm ready for that.
It's a lot to take in.
It really is. But thanks for taking us on this journey today.
It's been a pleasure.
You know, it really seems like we're just at the beginning.
I think so, too.
Of an incredible journey of discovery.
Yeah.
And who knows what mind-bending revelations await us in the future.
Who knows what the future holds?
I can't wait to find out.
Neither.
Thanks for listening, everybody.
Yeah, thanks for joining us.